This is Module 7C. Uh, in this sequence of modules, 7A, 7B, and 7C, we've been discussing the model complexity. And in 7B, we analyzed the optimal model class size. And that showed us that we probably want approximately square root of n quantization bins. And in this module, 7C, we're going to use a somewhat different decoding perspective. So suppose that we have two nearby parameters, theta1 and theta2, and we chose one of them, nature chose one of them. We then generated x, and the question is, given x, can we differentiate between theta1 and theta2? And specifically, maybe n needs to be quite large to be confident that we can differentiate, right? So this is analogous to decoding, differentiating between parameters and decoding between different communication messages. Well, this is similar. And what we're going to do, we're going to approach this decoding problem by computing the empirical probability and comparing it to theta1 and theta2, the two possible parameters. And to do so, in order to understand the possible performance, we're going to analyze the distribution of the empirical probability. So we're going to do this in several parts. We're going to begin by only looking at xn. So the true parameter is now theta. Later we can use our distribution understandings to decide between theta1 and theta2. But for now, true parameter theta, and we're only looking at xn. So the probability of xn being equal to 1 is theta. The probability that it's equal to 0 is 1 minus theta. The expectation or average value of xn is, well, with probability theta, I have a 1, so I multiply by 1. And with probability 1 minus theta, I have a 0, and I multiply by 0. 1 times theta plus 0 is theta. So that's the expected value. What about the variance? The variance of xn is the expected value of the square of x of n minus its expected. So now this expression inside the expectation, that x of n minus e of xn squared, we can break it up into three terms. The expected value of the square of xn minus 2 times x of n times the expected of xn plus the square of the expected value of x of n. In order to compute this, let's make an interesting observation. Xn is binary, it's 0 or 1, and so the square of x of n is equal to x of n. And this allows us to conclude that the expected value of the square of xn is equal to the expected value of xn, which is equal to theta. So now let's see what we have here in a text box. So we wrote that the variance was the expected, and should have been e xn square minus 2xn e xn plus the square of the expected value of xn. Now you'll notice that, as we've said a few times, the expectation operator is linear, and so we have the expected value of the square of xn minus 2 times the expected value of xn times its expected plus, well, the expected value of the square of the expected of xn is simply because the expected of xn is a constant. It's simply the square of e of xn. Okay, so let's start substituting numbers. The expected value of the square of xn, we said that that is equal to the expected value of x of n, which is equal to theta. We then are subtracting 2 times e of xn, which is theta, and the E of xn inside this expression, that's another theta, which is just a constant. This is 2 times theta square. And finally, we're taking the square of E of xn, which is again equal to theta. So we had theta, we subtracted 2 theta square, we added back 1 theta square. So overall we have theta minus theta square, which is equal to theta multiplied by 1 minus theta. Quick comment. Theta is in the range from 0 to 1. That means that 1 minus theta is also in the range between 0 and 1. And it means that theta times 1 minus theta, the variance, is greater than or equal to 0. And if you'll think about it later, you can evaluate that the maximal value of this product occurs when theta is equal to half, and at that time the product is equal to a quarter. So bottom line, what we've shown here is that the variance is equal to theta times 1 minus theta. Let's continue our discussion. That was the distribution of xn, now the distribution of n1 of x, the number of ones in x. Recall, we're headed to the distribution of the empirical parameter. We're not there yet. So the distribution of n1 of x, recall that n1 of x is x1 plus x2 plus x3 up to x capital N. So it's the sum of capital N IID Bernoulli random variables. And when we have IID random variables, the expected value of the sum of n of these is equal to n times the expected value of each of them individually. You could think of this as linearity of expectation. And we see that the expected value of n1 of x is n times theta. What about the variance of n1 of x? There is a result that you could think about later. The variance of a sum of n random variables is n times the individual variances of individual random variables, which is equal to n times theta times 1 minus theta. So we're now set up to look at the distribution of the empirical probability. We're taking n1 of x and we divide it by n. That means that the expected value is divided by n. It'll be equal to theta. And the variance will now be divided by the square of what we divided n1 of x by. We divided it by n, we're now going to divide the variance by n square. The intuition here is as follows. Standard deviation is square root of variance, and we are now dividing lengths by n, and therefore the standard deviation, which is in the same length units, is divided by n, but the variance is the square of that, n square. So we had n times theta 1 minus theta divided by n square gives us theta times 1 minus theta divided by n. So this n goes away, and we're left with n in the denominator. Bottom line, the empirical variance, and this is the important point, its variance is proportional to 1 over square root of n. So let's think about optimal decoding, optimal quotation marks, near optimal decoding. We're not doing this rigorously. If the variance is proportional to 1 over n, then the standard deviation of the empirical probability, which is the square root of the variance, is proportional to 1 over square root of n. This means that we can now differentiate between if the width of each of the empiricals around a true parameter is a width proportional to 1 over square root of n, then we can differentiate between something like square root of n parameters in the probability space between 0 and 1. And this brings us to regularization. The optimal coding length perspective in module uh, 7b showed us that Q, the number of bins, was proportional, similar to square root of n. And of course, the number of bins is the number of models. And the decoding perspective shows us that we can differentiate between something like square root of n models. So bottom line, something around square root of n is the sweet spot. And that's one parameter. What about k parameters? So the total size of the parameter space, we're going to have square root of n per parameter with k of these. So it'll be something like n to the power of half k. And the coding length required is roughly half k log of n bits. This is a result by Riesonen in 1984. More generally, we can think about in MDL comparing between different models that have different numbers of parameters, and we're going to want to regularize or penalize by the complexity implied by these parameters. So basically, for each parameter, you need to penalize by half log n bits. Different types of regularizers can be used. One of these is the half log n. It's only one approach. You can read about it later. So that completes the triple of modules 7a, 7b, and 7c.